Good evening, everyone. I'm Alessio. I'm a research engineer at Evolution AI. And today's talk would be about advances in value estimation in reinforcement learning, and will be given by Martha White, who is an associate professor at the University of Alberta. You can ask questions if you have any during the talk using Zoom's Q&A session that Martha will happily answer. But we'll also have a discussion at the end of the talk, and that will be facilitated by my colleague, Janielle. Without further ado, we can start the talk. So Martha, take it away.
All right, great. Thanks so much for having me. I'm always really excited to talk about our work in value estimation. So I know this is a smaller group. It's a meetup. It's a chance for us to talk about interesting topics. So please feel free to ask me questions as we go along. I've also put my slides in the chat so that you can go flip back to a slide if you're wondering something I said before. So you can follow along that way as well. So I'd like to make this interactive. I did try to make it a little bit shorter, but I also picked a pretty technical topic, particularly because I was asked to. So I was asked to pick a relatively technical topic as I would for, say, a workshop in machine learning. So I'm going to try to get across to you these really cool technical advances in value estimation. Okay, so I know this group knows a lot about machine learning, but I know it's also a broad group in machine learning. So I'll start by at least placing why value estimation is important in reinforced learning, and then we'll get to how we're going to do better at value estimation. Okay, so the reinforced learning setting. This is the standard reinforced learning setting where we imagine an agent interacts with an environment, and its goal is to maximize how much reward it accumulates. So you can imagine here you have this little robot. He's trying to control this power plant. And it might be in a state, let's say it starts in some state S0, it takes an action A0, like might change a pump speed, let's say. Then it's going to get back a reward for whether that action was good or bad, and it's going to transition to some new state. So the power plant will be now in some new state, and this interaction is going to happen continually. Okay, so the agent's goal is to take these actions so that it actually maximizes the long-term expected return. So the expected return here is written it like this. It says the return GT is the reward I receive on this step after taking an action, plus gamma times the reward in the next step, plus so on. So an infinite sum into the future discounted by some gamma that's greater than 0. And the agent's goal is to learn some policy pi that says in a state, this is how I take an action so that I'm going to maximize this expected return into the future. So here the expectation is explicitly conditioned on pi to indicate this is the return I would get if I were to run my policy pi. And now I want to find a pi that makes this expected return as high as possible. Okay, so that's our problem setting when we're trying to learn this policy. And so you can see since the goal is to estimate this, or to maximize this expected return, that is actually called the value function, and it's why value estimation is so central to reinforcement learning. So most algorithms rely on value estimation in some way. So let me just tell you what the value function is that we're going to try to estimate. So value function v pi tells us exactly this expected return that I just described. So it says if I was in some state S and I were to follow policy pi from this state, so I were to take actions according to policy pi, this is the return I would expect to see into the future. And sometimes we'll also write this recursively, where we can say that it's my immediate reward plus my discount times my value in the next state. And this formula makes sense because the value in the next state is also, again, the expected return now starting from that next state. So it's just taking the expectation inside. Okay, so it can be useful to have this value. Often we'll also want to have the action value function, which allows us to then get better policies. So an action value function says almost exactly the same thing, but it says if I was in a state and I were to take an action A, and then I were to follow my policy pi, what is going to be my expected return from there? Okay, this is a useful value function to have because it lets us decide in the state which action is going to have the most value if I then continue to follow my policy, so I can locally, greedily change my policy and get better value. So that's one of the ways we improve our policies, is to behave greedily according to our action values. Okay, and then there's other strategies that Q-learning is based on that directly estimate Q star, which is the action values for the optimal policy, and otherwise algorithms that are called policy gradient methods, or sometimes called actor-critic methods, also heavily rely on value estimates. So actually, I would say one of the defining characteristics of reinforcement learning are value functions and doing a good job of estimating them. This is a foundational question. Okay, so that sets up the problem. But I'm going to continue talking a little bit more about the background to this problem, what is value estimation and how are we going to tackle it? And then once I do a little bit of that background, I'll actually tell you an outline for the main 3 concepts I want to get across in the talk. And again, if there's any confusion along the way, please do interrupt me and ask a question. Otherwise, I'll just assume that you're following along. Okay, so continuing that. So that's the motivates why we care so much about value estimation. And now we're just going to go forth and say, all right, let's try to do a good job with value estimation. So the issue with this problem, like any kind of function approximation in machine learning, is that we're not going to be able to exactly represent b pi. And so now we're going to need to think about how are we going to approximate b pi. So instead, we're going to learn some parameterized value function. We're going to call it b hat. It has parameters w. And so for some given state, this is going to approximate our b pi of s. And our goal is to find this approximate values, and we want them to minimize this value error. So we'd like to be as close as possible to the true value function b pi. I'm going to start off only in the setting where we learn v pi, not q pi or q star. So this is called the policy evaluation setting, but all the ideas actually and the objectives extend to the control setting as well. So we're just going to start here because it's simpler, and then I'll show you how it extends. Also going to assume that we're looking at the finite state case, but again, the algorithms are not restricted to finite state. It just makes everything simpler to talk about, and we have sums and such. Okay, so this value error here is saying make the square difference small, and then often we'll have some state weighting where some states might be more important than others to get our value error lower. So this D is just putting some weight on our states. Now, the issue here is that we're not really going to be able to directly optimize this value error. And so a lot of the work in reinforcement learning for value estimation is trying to understand what objective function should we actually use to estimate these values. I'm going to start off with the most obvious one. It's not the one that we'll actually use, and I'll tell you, and so you can see why we're not going to use it. But one of the most obvious choices is just to use supervised learning and use regression towards samples of the actual return. So if we could get samples of a return G under a policy pi from our state S, then we could just go ahead and use pairs of those. I have a state, I have a sampled return, and then I'm just going to go ahead and do a regression update for that. So this is my function approximator. This is the actual return I saw, and so I'm going to do a regression update. So you might think, okay, we're done. Like, why is there even the rest of this talk? This seems like a perfectly fine solution. Mainly in practice, we don't use Monte Carlo strategies for estimating values, not usually anyway, for 2 main reasons. One is that in order to actually get these samples of G, we have to wait. So we have to actually run the policy for a long time until we finally have enough steps to get a good estimate of G. So that's going to delay. It's going to take us longer to actually update our value estimates. And the other problem is that these returns themselves can be high variance. And so even if you're okay with waiting, they still may not be the right choice. Instead, the much more common choice is to use methods that bootstrap. Okay, and so here the idea is instead of using actual unbiased samples of the return, we're going to use a pretty coarse approximation to the return, but it's going to work reasonably well, and we can also justify why it should work well. So the second option are called temporal difference learning methods, and these include methods called like Q learning that you may have heard of. And really, this is the standard go-to approach. Okay, so the TD update looks on the surface just like the Monte Carlo update. We still have some delta, that's like our error. We still have our gradient for our value function, but now we're going to replace the estimate of our G with a coarse approximation to G. It's definitely a very heuristic approximation. That's the skateboard. And so it says that the return is going to be R plus gamma times our guess of what the value is in the next state. So this guess, might be a little bit incorrect. Probably it's incorrect, but still it gives us an approximation to the return. And now we don't have to go sample an entire return. We don't have to delay updating. We can update right away. Okay, this is one of the reasons why TD methods are so popular. Okay, but now there's also some issues with this strategy. So even though it is the most standard approach, very common to use, it is only sound in a very limited setting, in the setting where we have on-policy sampling under linear function approximation. So off-policy sampling means that we are getting samples of data, like we're visiting the state space according to a different policy. And this is the norm, actually. Almost always do we have off-policy sampling because we'll usually keep a buffer of old data and use it for what's called replay, where we're going to constantly replay over this big batch of data to update our estimates. And that data is from old policies often, and so we're going to have off-policy learning. We can also diverge under nonlinear function approximation, which again is going to be the standard setting. We're often going to want to use things like neural networks. We're not going to want to be restricted to linear function approximation. Okay, and so you might wonder why TD is not sound. It is very widely used. The update looks like it's sort of reasonable, and the TD update is not sound because it's actually not the gradient of any objective function. So here I'm just reminding you what the TD update looks like. Okay, and you might think maybe it's the gradient of this delta like it usually is for regression, but actually it's not. So if we were to look at what the gradient of this error term is, delta squared, and we just take the gradient, we'd have a delta. I missed the 2 here, but we'd have a delta, and then we'd have the gradient of this inner term here. The reward is not dependent on the weights, but these 2 terms are. So we'd have a gradient of this term minus a gradient of this term. Okay, now TD is not using a delta times this term here. It just omits that term completely. So it's definitely not the gradient of this squared TD error. It is, however, still a reasonable algorithm. There's a reason people have used it there, and there are soundness arguments in some cases. And the reason is that in the linear function approximation, TD is actually a stochastic update for a linear system of equations. You can see it as a stochastic iterative system solver. And so in that setting, in the linear setting, we can actually say certain things about the properties of the linear system and why that iterative system solver is actually going to converge. But once we move beyond the linear setting, it becomes hard to say anything. Okay, so like I said, TD is a very widely used method, continues to be very widely used, as is Q-learning. And so we know that it may not be sound, but how does this really manifest in practice? Like, do we really care, I guess is the question here. And so we might ask, what does this look like in practice, this unsoundness? What we have found is that actually TD is just generally a pretty great algorithm. There's a reason it has stood the test of time. So it generally performs very well until suddenly it doesn't, and it really does do something like diverge. Okay, so this is a pretty complicated plot. Let me just explain what's happening here. What this plot is showing, these are just very small little micro worlds where we test some of these algorithms. I'm not going to take the time to actually go over them. I just want to point for you overall what happens with some of these algorithms. So TD is this blue box here. Everything is with relative performance to this orange algorithm. That's the algorithm I'm going to talk about in this work. It's a better gradient TD method. And the blue one is just generally, TD is just generally good until suddenly in this counterexample called Bayes' counterexample, it actually diverges. So its performance shoots off and it has a terrible error on this problem. So that's typically actually what we see with TD. Generally it does pretty well, and then sometimes something weird happens. Well, a couple of other things that are sort of neat to point out on this slide is this problem has been recognized. I'll tell you a bit more about some of the solutions that people have been taking. 2 of those solutions are these things called GTD2 and TDC. They're standard gradient methods. But if you'll actually already notice here, GTD2 and TDC, these algorithms, just generally are always worse than TD. And here is quite a bit worse than TD. And so it sort of motivates why it is that people seem to have generally avoided these, and that TD continues to be the algorithm of choice. So they're sound methods, but they don't seem to work very well. That's why we've really been looking at how can we get better gradient TD methods. You might also wonder, how about in control? How does this manifest with something like Q-learning, which also has similar divergence issues? It's based on the very similar update that TD has. And so there are some counterexamples for that one as well. And in our own experiments, what we seem to have found is that Q-learning can be quite sensitive to its hyperparameters. So again, using 2 little small classic environments that we often test these things in, called Mountain Car and Lunar Lander. QRC is like that better gradient TD method, but now for the control setting, this is our method. This is Q-learning, so a standard Q-learning update in these problems with neural networks. And Q-learning can do okay, it doesn't do as well, but it can do reasonably well, but across different hyperparameter settings. So that's what these plots are showing. They're showing you performance when we plot across all the different hyperparameter settings. Performance is very variable for Q-learning and less variable for this gradient method. So that could be the other way that sometimes these soundness issues are manifesting in practice. So my main point here anyway is that it's a serious issue and something that we need to actually deal with. So how are we going to improve on these TD methods? So unsurprisingly, this has been a long-standing problem. So there's actually been a lot of work on this. And this talk, in some sense, is a synthesis of all those insights. And I think finally some real answers where we can start using these algorithms in practice. So there's a long history of approaches for value estimation. And many of these approaches actually correspond to minimizing 1 of 2 typical objectives. So I'm just going to tell you about those objectives rather than about the many different algorithms that exist out there. Okay, and so this is sort of where now I'm actually going to start diving into more of these technical details. So I'll give you an outline of what's now coming up. So the first part here, mainly, I just want to emphasize to you, like, why do we care about value estimation and what are the key problems when it comes to value estimation? Okay, and now I'm going to tell you a little bit of a history of what has been done for value estimation, particularly by telling you about these objectives and why they are still limited. Then I'll tell you about our new generalized objective that helps, generalize to the nonlinear setting, and it fixes some of the issues with these previous objectives, really kind of unifies and fixes. And then finally, I'll tell you about, even with this new objective, which does help us get better algorithms, the naive algorithm using this objective doesn't work that well, but we have some ideas that really improve on it significantly. And I really summarize that as how we finally got gradient TD methods to work well. So that's my main goals for this talk. Okay, so diving into some of these details. So let's look at a little bit of the history of these two objectives. One of the most standard objectives that's been considered is called the squared Bellman error. Okay, and the Bellman error comes from the fact that we know the true values v pi satisfy what is called the Bellman equation. So we have a Bellman operator T that takes our value estimates v pi. Let's take the value function, let's say v pi here, and it is an operator that gets applied to v pi that sends it to r plus gamma times v pi in the next state. Okay, so this operator is taking these v pi, and then when we query it at s, it's exactly equal to this thing. So when v pi satisfies this Bellman equation, it's equivalent to say that v pi satisfies this equation, that v pi at s should be equal to the expected reward plus gamma times value in the next state. And that makes sense because, again, this is the expected return in the next state. So for v pi to equal the expected return, it has to equal this formula as well. Okay, so we know that v pi satisfies this. Our goal is to estimate v pi. And so we are going to try to leverage the fact that v pi should be equal to tv pi. So under function approximation, we typically won't be able to find v is equal to tv. We won't be able to satisfy this equation for every single s. There's going to have to be some trade-offs. So instead, we're going to try to minimize the distance between v and tv. So that's what the Bellman error is. The mean squared Bellman error says, I'm going to apply my Bellman operator to v hat, and I'm going to look at the difference between my Bellman operator applied to v hat minus v hat, and I'm going to take the squared difference. Again, we're going to sum over some weighting over states, just like we had for the value error. And we'd like to make this difference small. So essentially, I want to make the difference between v and tv as small as possible. And then hopefully that's going to get me closer to a v pi, because we know v pi would have a mean squared Bellman error that's equal to 0. So the smaller we can make this mean squared Bellman error, hopefully the closer we are to v pi. Okay, we can rewrite this kind of ugly looking thing, and we're going to rewrite it in terms of these TD errors. So the TD error is the thing that we've been talking about so far with TD, where we look at r plus gamma times the value in the next state. So that's our estimate of the return minus v. And so this can be perfectly rewritten just saying the Bellman error is the expected TD error squared in all of our states. Okay, this is a pretty important objective. Bellman equations are very important also for estimating value functions. But now an issue with this objective is that it has this problem called the double sampling problem. So in order to get an actual unbiased estimate of the gradient of this objective, we need 2 independent samples from a state, which means really we're restricted to having a setting where we have a simulator, and we want our algorithms to work beyond just the simulated setting. So to explain that just a little bit more, let me point out why this again isn't just an objective, that's the answer. So just rewriting again for you here what the Bellman error is, and looking at the gradient of the Bellman error, just using standard chain rule, the 2 comes out in front, we have this expected Bellman TD error here, and then we take the gradient of this inner term. Okay, now the issue with this gradient is that we have the product of 2 expectations. And whenever you see the product of 2 expectations, you might start groaning because you're going to see that this is going to be hard to get an estimate of this gradient. So imagine if we were in a state S, we then transitioned and got a state S prime and R, and we just tried to use this as our sample of the gradient. So TD error times gradient of TD error. Well, that's not going to give us an unbiased sample because we know the expectation of this product is not necessarily equal to the expected value of the first term times the expected value of the second term, i.e. expected value of x times y is not equal to expected value of x times expected value of y, unless x and y are independent. So we'll need an independent sample for this term and an independent sample for this term, and that's the double sampling problem. I'm going to pause here in case anyone has any questions. If you want to, pose a question in chat or in the Q&A. All right, there's no questions. I mean, we do have a lot of time at the end to talk more about these, so I'll keep going in that case. I will say an aside here, one of the things when we talk about value estimation is it's, there's always a, well, if you have this problem, why don't you just do this thing? So as an aside, you might just ask, why don't we just use the square TD error then, since the mean square Bellman error is such a pain? So that would mean just instead of having the squared on the outside of this expectation, let's bring the squared on the inside of this expectation. This has a name, it's called the mean square TD error. Taking the gradient is easy. It's actually easy to get an unbiased sample of this gradient. We just talked about how it's easy to get that. It just wouldn't give us an unbiased sample of the mean square Bellman error, the gradient of the mean square Bellman error. The issue is that even though this is easy to use, in general, repeatedly, we have all found that this generally produces pretty bad solutions. So we're not going to take the route of taking the square TD error. And there's some good arguments in the paper that's the basis for this talk, telling you why the square TD error might not be very good. Okay, so let's go to the other objective that's typically considered. So the squared Bellman error is, was introduced long ago. It has been used by some, but in general, it was hard to build on because of this double sampling issue. And then more recently, in 2009, the linear projected Bellman error was introduced as an alternative objective. And the really neat thing is that it was the first time someone pointed out what the true underlying objective is for the temporal difference learning methods. So even though TD is not optimizing an objective, when it converges, it actually converges to the solution of the linear projected Bellman error. So a new objective both helped understand what the properties of TD are, but it also helped us down to say, okay, if we know what the underlying objective is, now we could try to optimize it with different optimization strategies. So the introduction of this really resulted in a huge set of different methods being introduced. I'm going to make a guess, like 20 different methods being introduced from this objective. So the idea is just a little different than the mean square Bellman error. It says that instead of trying to find V is equal to TV or minimize the distance between V and TV, the Bellman operator applied to V, we're first going to apply the Bellman operator to V, and then we're going to project back into our space of representable functions, in this case, linear functions, and then we're going to try to find this fixed point. So the formula looks pretty similar to the Bellman error, except instead of only having a Bellman operator applied to V hat, we have now the projection times the Bellman operator applied to V hat. So we have a slightly new operator here inside the projected Bellman error. That's why it's called projected. Okay, so like I said, there's lots of great things about this objective. It also results in lots of really great research, but one issue is that it's restricted to the linear setting, and a few other issues have been highlighted that sometimes it can actually produce poor solutions as well. So we have these two great objectives. They have some nice properties, but they also have some limitations. So in general, summarizing this larger history and the motivation for trying to do something new is, TD can diverge in the settings that we typically care about, which is off-policy sampling and nonlinear function approximation. We don't want that. We want sound algorithms. There's been lots of progress made with dealing with this problem since the introduction of the linear projected Bellman error and all the gradient TD algorithms. But the issue with the projected Bellman error is that it has been restricted to the linear setting. There was one extension to the nonlinear setting, but it was pretty complex and it was not widely adopted. And otherwise, the Bellman error doesn't have any such issue about being restricted to the linear setting, but it, on the other hand, has this double sampling problem. Plus, Rich Sutton has also pointed out a few identifiability issues with the Bellman error. So pros and cons to both, but some issues with both. However, really recently, the Bellman error, I'll say 2017 or 2018, someone proposed a really neat strategy to try to start dealing with this double sampling problem using this conjugate form of the Bellman error. And that idea is exactly what we rely on to introduce our new generalized objective. Okay, so that's what this talk is mainly going to be about. We're going to use the same conjugate form to develop a generalized projected Bellman error. And then given that projected Bellman error, it's going to help us develop new theory and new algorithms. Particularly, also, we're going to leverage insights from work on the linear projected Bellman error and the Bellman error, because this generalized projected Bellman error unifies these two settings. So it helps us draw from both of those literatures to get both new algorithms and new theory. And this is all associated with this paper that was just published in JMLR with my PhD student, Andrew Patterson, called The Generalized Projected Bellman Error, this long title here. And then we also have an extension to Huber losses that I'll mention at the very end of this talk that's currently up on arXiv because it's in submission. Okay, so let me tell you why this generalized projected Bellman error is so cool and how it lets us actually get some good algorithms. So we're going to do that by just deriving this objective, and the derivation is very simple. So this conjugate form is quite lovely. It was introduced actually by Bo Dye and others, and as soon as we saw it, we thought that is a very elegant idea. We need to exploit that for ourselves. Okay, so the idea is as follows. We've already seen that the Bellman error looks like this. We have an expected TD error given a state. And now what we know about the squared function is that we can always rewrite the squared function using its biconjugate. And this biconjugate looks like this. So we can rewrite it by introducing an auxiliary variable h, and that it just looks like this. Okay, this doesn't look very useful yet, but we're going to see how it's useful for us in a second. So for us, y is going to be this term here. And so this is our y squared, and we're going to plug in 2yh minus h squared here. So this is our 2yh minus h squared, and we're going to maximize over this auxiliary variable h. Okay, that's step one. Step two is that we're going to pull this max outside of this sum by just noting that we need to have an h that's different per state. And so we couldn't just say we're going to learn a function h in the space of all possible functions, so it's not restricted in any way, where you can learn a different h value for each state. So these two things are equivalent because we're not restricting our function at all. I see a question here from Theodorus. What is a good book you can suggest on reinforcement learning? I mean, the best book I think you can have for reading for reinforcement learning is Rich Sutton's book, and he does have a second edition. Actually, I recommend the first edition if you want to read a shorter version to start, and then for more details, you could actually go to the most recent edition. Great. Okay, so this is mainly it. This is how we've reformulated the Bellman error with a conjugate form. And now there's the so what. Why is this a useful thing to do? Well, this is useful because now we've changed the Bellman error from having this annoying square term here where we have a double sampling problem to instead now optimizing over an additional auxiliary variable, but we've removed the double sampling problem. So for a given h, if I were to hand you an h, this auxiliary variable, computing the gradient update for the main weights now is just straightforward. So to see why, I'm just going to define this little function c, like c for an objective or cost. That's exactly that inner term for our Bellman error that we just derived on this 2yh minus h squared. We're going to rewrite the Bellman error with this cs here. And so now for a given h, here, when we compute the gradient of this inner term, then the derivative, this term just falls away. The derivative of the first term is very simple to compute. It just corresponds to this thing, and we multiply by an h of s. So the stochastic gradient update for w for a given h is very simple to compute, no double sampling problem. And then of course now we have an auxiliary variable, so we also have to optimize that, but that's also straightforward to do. In fact, what we can show is that the optimal solution for h is to estimate the expected TD error given a state. And so to update this h, we just need a simple regression update where we use delta as a target. So we now have an extra auxiliary variable, which, is a bit of a pain, I suppose, but we have at least removed this problem, and now we have simple algorithms to update both w and h. Let me just show you mechanistically what that actually looks like. So what this would look like is, let's imagine you're doing TD. We're going to input some state S. It's going to go through your neural network that has these parameters W, and your goal is to output an estimate of the value function. So we have a V hat here. Now what we have to additionally do, so TD would also include this green part. Now we additionally just have to have this auxiliary variable. So we're going to add an extra head to our neural network. That's going to also estimate our H. Okay, our H estimate is going to say for my given state, I'm going to do a regression update towards the TD error delta for that time step T. And for the update for W, it no longer looks like the TD update anymore. There's not a delta times gradient of V. Rather, it has this form that I just showed you. It takes our current estimate H and it multiplies by this gradient of our delta. Okay, so it's actually a very simple thing to implement. The updates change a little bit and we have an extra head on our network. And the same thing would be true also for the action value setting. Just now we would have to have different estimates for each action as well. And the same is true for the H. H would also have to be now a function of states and actions. We'd output a different estimate for the expected TD error given a state and an action. Okay, great. And I very much appreciate the question, Kelvin. So there's a question here about why is the substitution y squared is equal to y times h minus h up to valid? Okay, I'm going to scroll back up to that for a second. Why is it valid here to use this formula? This formula is just a true fact about the squared error. And I guess I can tell you the underlying reason. The underlying reason is that if you take a function, a convex function, and you then take its conjugate, and then you take its conjugate again, which is called the biconjugate, then for certain cases, in this case for functions like the squared function, the conjugate and the biconjugate are actually equal to each other. So that's how you get the right-hand side. You take the function y squared, you go compute its conjugate, then you go compute the conjugate of that, and you know that those two, the original function and the biconjugate, are going to be equal. Great. Okay, like I said, we can also use the same idea for Q learning. And mainly what changes is the TD error update changes, but otherwise the updates look very similar, and we just have to add these additional heads. So mechanistically, it's pretty straightforward. So that could be what the new algorithm is, but it's good to step back and say, okay, wait a moment. We're supposed to be talking about an objective here and having sound methods. When we reformulated the Bellman error, we had this H in the space of all functions. But once we have this neural network and we have this H as an extra head, we're actually approximating H. And so we may no longer be optimizing that true Bellman error, which requires us to go get that true H. And so we might ask, what are the ramifications of approximating H? And is it actually an okay thing to be doing? And what are we really doing? So the neat thing here that we show mainly in this paper, and which leads us to our generalized projected Bellman error, is that if we start from, if we replace H in the space of all functions, and we now constrain it, we're going to pick a function space for H, the set of linear functions, or let's say two-layer neural networks like we had on the last slide. We're going to look at what does this formula become. So if I had H and F all, this would be the Bellman error that we just reformulated. And now I'm going to constrain F all to be just H. Okay, I'm going to skip all the steps. And what we'll eventually find is that this formula actually ends up looking like a projection on the differences between our Bellman errors. So this is the Bellman operator applied to V hat. This is the difference to V hat. This is the thing we saw before for Bellman errors. And now this is a projection operator. So this math looks a little different than it did before, since we need to actually write this by thinking about vector spaces and how we're going to project things. But the general idea here is that we now take this Bellman error and we're projecting those errors away depending on our function space H here. So our H is actually going and taking our errors and projecting them to whatever our function space is for H. So that's what this projection operator is here. So in fact, that's why we call it a generalized projected Bellman error, because we still have Bellman errors and we are projecting them. It's just that we're now changing what that projection operator is. And in fact, this generalized form is going to include each of these as subsets. So this is sort of the general idea. You can go look at where we actually derive this. But what's most relevant for us is that now our generalized projected Bellman error is this equation. We're explicitly saying that it's defined where we're going to replace H with, we're going to replace this maximization over all functions with this specific function. And now for different choices, we're actually going to recover some of these objectives we had before. So if we picked this new space H and our space for our value functions F to be linear functions, then we get back exactly the linear projected Bellman error. If we pick both of those to be the same and for them to be nonlinear functions, we actually get a very natural extension of the previous projected Bellman error now to the nonlinear setting. If we pick H in a certain way that we talk about in the paper, then we're going to actually get back now what we're calling the identifiable Bellman error. So it helps resolve this identifiability issue with the Bellman error, but it pretty much gives you back this Bellman error that you would have wanted originally. And then otherwise, there's a whole space of different options that we could explore that we haven't gotten to explore yet. There's many more things to be done there, but to understand what this H should be. Okay, so I'm going just a little too slow, so I'm going to speed up now and get to the next thing here. So the main answer to this question was, once we approximate H, we're no longer minimizing the Bellman error, but it is actually still a perfectly sound thing to do. So approximating H means now we're actually optimizing this generalized projected Bellman error, and that's a good thing too. So we're happy to be optimizing this generalized projected Bellman error. Okay, and this nice question here from David: is the math used here for biconjugates and projecting into vector spaces something that would be learned in a convex optimization class, or is a different type of math where one would learn this? Okay, that's a good question. Would you learn in a convex optimization class? See, I've never taught a convex optimization class. So sometimes it's not something that I would necessarily have learned in a class. Maybe you're reading papers, you see this trick that's used for biconjugates. So then you go learn about biconjugates yourself, and then you start using biconjugates. So I mean, maybe the stuff about biconjugates might be taught in either a classical convex optimization, that's possible. Also possibly a course on just a regular math course on functions, like functional analysis or real analysis might have things about that. Sorry that I can't answer your question better, David. I can only answer how I learned about it. I learned about it by seeing it in a paper and then going and reading about it by myself. But I did actually take a lot of formal courses on function spaces and such too, so I would have seen conjugates there. Okay, so we have our objective. It's nice and sound, but now the next question we can ask. So that's the introduction. That's the second part about introducing our objective. Now we want to actually use it to get better algorithms. So the next question is, how well does it work? So when we use the straightforward gradient descent update, actually we find it doesn't work very well. So this is that update I've been telling you about this whole time, where we just assume we are given an h, we take the gradient, and it's the most straightforward choice. And I also think this is maybe one of the reasons gradient methods hadn't been adopted very much, is because, again, the straightforward update we have consistently found does not work very well. And maybe one intuitive reason you can see why it might happen is it relies very heavily on your estimate for h. So the whole update is modulated by h. You know, imagine you initialize your h to 0. That means none of your weights are just not going to be updating for a while because you're multiplying your update by 0. So what we're going to do is do two things to make this algorithm more practical and particularly reduce our reliance on this estimate in h. So actually, even from the earlier work on linear projective Bellman error, which is where we get this idea about how to have a different, smarter algorithm for the generalized projective Bellman errors, we can sample the gradient in two ways. So the saddle point update is that naive, or the straightforward way, maybe not naive, but the straightforward update. And then another update that's been considered that seems to work better is called the gradient correction update. Okay, so the main difference between these two is that notice the second term is the same, h of s would multiply here, so this term is exactly the same, but the first term is a little bit different. Instead of using h of s here, which is this h of s is trying to estimate the expected delta, we're just going to use a stochastic estimate of delta. Okay, so this is actually giving us an unbiased estimate of delta, whereas h of s is an approximation, so it's going to give us biased. So you can kind of see how this might be a better choice. And one motivation for why this is okay, or where this is coming from, is if we actually go back and look at the mean squared Bellman error gradient, it had these two terms. If we were to plug this gradient in here, and then we were to multiply the first two terms and the second two terms, notice the first term, since we're given s, is not actually random. It's a deterministic value, so there's not going to be in an expectation. So we're going to have just the gradient of v times expected delta. And then here is where we actually run into the double sampling problem. So double sampling only comes in because of the second term. So we can use the h of s, which helps us deal with the double sampling problem only for the second term. And for the first term, we can actually use an unbiased sample for the delta. So that's one motivation for why the gradient correction update could work. It's actually not the real reason for it. It's more of an intuitive argument. There's another argument about plugging in the true values for h that lets us also get this update. So again, go look at the paper if you'd like to understand a bit more about that. But in any case, what we have found is the gradient correction update is much more effective. The first update is not very effective. The second one is much more effective. And one of the reasons is TD is really good. The first term here is like a TD update. And then this term is really just correcting the update. That's why it's called a gradient correction. So if h of s is sort of small, this is just slightly modifying the TD update. So we're taking a pretty good update and then we're just improving it by making it a little bit more sound. I think that's one of the reasons gradient correction works well. And the other thing we have found that made this update much more effective is so the gradient correction is much more effective, but even that on its own was still not enough to get a very good gradient algorithm. The second thing that we found was really key. It was a very simple idea, which is that we needed to actually regularize this variable h so that it was constrained a little bit more and didn't skew this update too much. So the original algorithm we introduced was called TD with regularized corrections, since we regularized this h, and then the corresponding control algorithm, Q-learning with regularized corrections. And then later we found that one reason that seemed to help so much might be actually because it's connected to using a Huber loss. So in this other paper that I mentioned that's now up on arXiv, we have now taken this general strategy where we use these conjugates and biconjugates, and we've said, well, we don't have to use squared Bellman errors. We could actually use robust errors instead, like absolute Bellman errors or Huber losses for these Bellman errors. And if we do that, So I'm just telling you what a Huber loss looks like. It kind of looks like squared near the origin, and then it becomes something like an absolute value. If we use those more robust losses, actually the resulting objectives look actually a whole lot like our mean square Bellman error. And the only thing that changes is that the space over F for the space over H is now just more constrained. So you're not allowed to pick any H. You have to pick an H in this clipped region. And that is going to give you a lot more robustness. So regularizing H was playing a similar role, we think, to doing this robustness. And then in our experiments, we definitely found that adding these constraints on H had a significant effect on improving performance. So this is almost my last slide. I'll summarize here what this is showing. So again, these are just some simple worlds we like to test these algorithms on. DQN here is run with target networks, our algorithms, which are called QRC, and then our modification that also uses Huber loss instead of the squared loss are not using target networks. If you don't know what target networks are, it doesn't really matter. So you can just think of this as standard Q learning, and this is our algorithms. And the neat things to notice here are that generally QRC Huber, the one that uses a more robust loss, is consistently the most effective. So this black line is generally just doing well across these problems. QRC is generally also doing okay, though sometimes not as well. So maybe it's not constraining that H as well. And sometimes the Q learning method does perfectly fine. And then other times it really is failing quite badly. So if you'd like to see a little bit more about this, we have this paper up on arXiv called Robust Losses for Learning Value Functions. Okay, now here there's a question from Vincent. Would the updates of W and H somehow conflict each other, making the learning unstable, or is the stable guaranteed by the properties of the biconjugate? Okay, that's a great question, actually. So when in practice, when we're actually going to use these methods, we're going to be updating W and H at the same time. H is an approximation. Maybe there's going to be some feedback loop between W and H that causes problems. Actually, the original proofs that split it up and added these auxiliary variables did require that to be carefully controlled. They had a slower time scale for W and a faster time scale for H. So they said, imagine H is changing fast enough that it is actually becoming close to a good approximation of the expected TD error before it's used to update W. Later, though, actually it was found you didn't have to do that 2 time scale thing. They can change together and it's no problem. And one of the reasons for that is that it is just solving a min-max problem. And so, in that literature, we know that we can actually change this W and H at the same time scale. Nonetheless, you are right. Of course, in practice, they are going to have some impact on each other. And even in that neural network architecture I showed you, we chose to have H have a stock gradient right at the last layer, so it didn't backpropagate through the network. So the network was focused on the updates for W. So it was adjusted primarily for a value function estimates, and H was just added as an extra head that didn't mess with the values in the neural network. And we generally found that performs a little bit better. I hope that answered your question. Anish, how are we choosing H of S, and are there any domain-specific assumptions taken whilst choosing it? Right. I think the choice of H is one of the most exciting open questions, actually. We chose it like I just said. We took our whatever neural network we used for W, and we just added H as an extra head on that neural network. We did try a few other things where we separated out H out and let it be its own neural network. We let it be a simpler function. We tried a few other things. So I don't have an answer for you yet. It's definitely domain specific. Very reasonable choice is just to make H an extra head on that network, like I said. So it essentially has the same function approximator that W has. But there is reason to believe that it should be different. It's trying to actually estimate the expected TD errors, the errors themselves, whereas W is trying to estimate the value functions. You can imagine those function classes have to be different. Okay, so the key takeaway from these results and generally this section is that we can actually get gradient-based approaches that improve on the standard TD algorithms that are much loved, but we only really get these if we use the gradient corrections form of the update and if we also constrain our auxiliary variable. Those two things seem like they were key for getting improved performance. So overall, the summary of everything I've said here is it's an exciting time. We actually get to improve on TD and Q learning. These are great foundational algorithms, but we can do better. That in itself, in some ways, is surprising. It's always surprising when you can improve on algorithms that have stood the test of time. One of the ways we can do this is to get this new objective called the generalized projective Bellman error, which extends and unifies the previous linear projective Bellman error and the previous Bellman error. And I think it just provides us a better alternative to both. And finally, the last point is that the actual resulting gradient algorithms you get from this objective really do work. And I think we should start considering using them, swapping them into our reinforced learning systems. And additionally, we can actually leverage this larger literature to get both new algorithms and theory for these gradient algorithms. All right, thank you very much. And I hope you have more questions for me.
Great. Thank you very much for the very interesting, very detailed talk. As a reminder to everyone, if you want to ask any question, you can use Zoom's Q&A button. And if you want to ask the question yourself personally, you can use the raise hand functionality on top of adding the question to the Q&A. Now we can have about 15 minutes of discussion. So I'll let the stage to Shaniel.
Yeah, thanks. And thanks, Martha. That was a very interesting talk. And we had great questions from the audience already. So that's always good. Let's see. I don't see any questions right now, but I do have some questions myself. And, reinforcement learning is a far off land for me. So I have very down to earth questions. One of them is these weights that you have in the norm, for example, in the mean Bellman error in your slide 17. You have this DS. It also shows up in the value error itself. And if you could tell us a little bit more about that, because in some of these problems, like you're working with very large spaces for the states. And this DS is going to determine like the geometry, basically, of the value function. So if you could tell the choice for DS is a way, like what restrictions you put in DS, like is that something that is given by the problem itself, or?
Yeah, it's a great question. Actually, there's some hidden slides here that I knew I wouldn't have time to talk about how important this choice of D of S actually is. So let me tell you a little bit about what it is. One thing you might just say is, why don't we just not have a D of S there? Why not just sum over all states? I guess the first place that D of S actually comes from is from the problem setting. So originally D of S, we would usually think of it as, if I'm running my policy pi in the environment, it's going to visit states at a different rate. And so my D of S is actually going to correspond to my visitation frequency. And if I visit states often, I probably want my value estimates to be accurate there more. So I'm going to have a higher weighting on those states that I visit often. So D is sometimes called D pi of S in our value error, where we put higher weighting on states that are highly visited by the policy pi. But it is hard to say exactly where you want your states to be accurate. So in the value error, it is sort of up to the problem designer to decide which states do I really want these value estimates to be accurate. It could be based on state visitation. It could be based on other criteria. The second part of that also, though, is that sometimes it's not just part of the problem. D of S can actually also be part of our solution. So you might imagine there's some true weighting you care about for your states in the value error. And now in the projective Bellman error, it's a surrogate objective. It's not directly minimizing value error. We have found some cool results where picking D of S, you don't want it to equal to the same thing you have in the value error. You might actually want it to be something different, and it gives you better solutions according to the value error. So it actually does play a super important role. It also plays a super important role when it comes to convergence and divergence. That's one of the reasons TD diverges actually is the choice of this D sometimes. So your question is a very good one. There's a very technical answer to it.
So is it possible to have then DS be parameterizable as well, so we learn what this norm is as well?
Okay, so let's say we wanted to minimize so let's say we knew that there was some true value error D, like I just wanted to, let's use D pi. That's always the easiest one. I really want my accuracy to be high in the states I visit often, sort of sensible.
Okay.
And then is there a way I could learn the corresponding D in my projected Bellman error that would help me maximize the value error? I don't know, actually, maybe. I don't know if I've ever seen anyone do that before. We have just some theoretical ones that seem to be true. There's these new weightings called emphatic weightings that we have found actually does help us do a better job of optimizing value error. But otherwise, again, just like how do we pick H, I actually think that's another pretty cool open problem, is what should D be in our solution side.
Okay, I see. Good. Yeah, thanks. Well, we have another question from the audience.
Okay, right. Our target network's expected to also address the issues here. Yeah, I didn't really get a chance to talk about target networks. I do think I had this speculative claim earlier on that I think that the use of target networks has been important, maybe because of the instability in Q learning. You'll hear I said very speculative, may also explain the need for target networks. Let me just tell everyone here what target networks are. If we go back to this TD update, I told you that TD dropped this component. Target networks say, instead of using my current value estimates in my return estimator here, this approximation, I'm just going to use a different function. I'm going to use my value function from 100 time steps ago. It's fixed, it's not changing. It's going to be plugged in here. And so when I take the gradient now of this delta squared, this term no longer depends on my current W. And so I'm actually not omitting any terms. I'm just taking the gradient of a changing objective function that changes as my target network changes. So it's called a target network because it's part of your targets. It's not your current weights, and it's usually some outdated network. So in that sense, you could imagine it helps address the soundness issue because now we at least are taking the derivative of a fixed objective function. It's just that that objective function changes over time. There isn't a lot of theory that says that target networks now make TD sound, but there is one cool paper that tries to tackle that. So going back to do target networks address the issues here? I do think that target networks help us address the divergence issues of TD to some extent. But one reason I don't think that they're the right solution is, first of all, we don't really know what they're doing because the objective changes with time. But also the beautiful thing about bootstrapping is that you take your current value estimates and you use them to tell you, what do I think is my return into the future? If you're taking old value estimates that don't have the most new data incorporated, in some sense, you're choosing to pick a worse estimate for your return to bootstrap off of. There's something inherently wrong about that to me. So I think that target networks can actually slow down learning. And in our own grading algorithms, all the results I showed you later, we did actually try adding in target networks, and it did in fact just slow down learning. So we didn't need that extra stability boost, and it was worse to use target networks. So I do agree. Target networks are somehow playing a similar role, but they're doing it differently. And time will tell which of the strategies is better when.
While we wait for another question, I actually have another question myself, and it's related to your slide number 20, and there again, I have a naive question here. It's like, why is this? What number am I looking at? It says 20. That's not. Yeah, that one. Yeah, exactly. Yeah. Yeah. So my question here is like, it's a converse of this. Like naively, why would one try to use the mean square TD error as a function you would try to minimize over? And the reason I'm asking is because the form of this TD, this temporal difference between the value function at the next state and the current one plus the current reward doesn't have, and you square that, doesn't have the shape that we're familiar with in this function these differences, these norm differences that we usually minimize over, like the one, for example, the Bellman error has that form. In this case, we don't have that shape. So why would I think of using this method?
Okay, I got it. Right. Yeah, I said it was the natural thing to do. I think the reason it would be natural to think of using this strategy is that it kind of looks like what we do in regression. So in regression, we say we're going to take the mean squared error. And so we take the squared error. And the error for us in some sense is like the TD error. And so then we're taking the squaring and we're taking the expectation across all possible states. So what would this look like in regression? In regression, we'd be summing over all x. Let's say it's a sum instead of an integral. So we're summing over all x. And this expectation for a given x would be over all y, because there's still going to be some stochasticity in y as well. And so, for regression, we would have y minus f of x squared. So the squared would be on the inside. So that's why I think it's kind of a natural way to do it. Whereas we have the squared on the outside, we take like the expectation over y first, and then we take the squaring of that. So we're taking the expectation of our return first and then taking the squaring. The reason in the regular linear regression setting or the regular regression setting is that those two objectives are actually equivalent. I believe they produce exactly the same solution. So in fact, in regression, you could have put the squared on the outside. There just would have been no point. For us, though, it matters because the squaring on the inside is now you look at the difference between r plus gamma times value in the next state minus phi. And so you're actually looking at the stochasticity and rewards in next states. And you're trying to minimize the expected squaring when you take into account stochasticity over next states. Whereas when you take the x squaring on the outside, you first average overall stochasticity in the next states, and then you take the square difference. So they really have very different interpretations. But that's what we were asking. You weren't asking why is it a bad thing to use. You're asking why would one even consider using it. Did my first answer clarify? Okay.
Yeah. Okay.
Okay, there's a question here from Anish. Is there any way to deal with d pi if pi changes over time? Say if an agent chooses to change the strategy mid-game. Oh yeah, great question. So everything throughout here, I have assumed that d of s was fixed. And I said we're going to do policy evaluation. And then I did imply that everything extends in the control setting. I totally agree that in the control setting, our policy is changing all the time. So the data you're actually gathering is changing. And even the states you care about might be changing. So your d might be changing. We, again, have no way to deal with that problem. Right now in the control setting, we've imagined that someone hands you, let's say like a big replay buffer or a big batch of data, and the D is implicitly defined by that batch of data. So if your buffer has, you see these states more often and these states less often, you're going to sample uniformly according to that buffer. And so implicitly your D is just given by how much you see certain states in that buffer. And so we're not imagining that we change that D. But you're right, the objective changes with time. I hope that answered your question. And it's another cool research question about what does it mean for our objectives if our objective is changing because our D is changing. If you had another question about that, Anish, please ask. Okay. Renee, do you have a reference? Something to help find out the paper on target networks. Oh, the one that proves stuff about it? Okay, it's a paper from Dongwei Li and Niao, how am I forgetting her last name? Okay, it's what would the paper be called? If you just look up convergence of periodic TD or something like that, you should be able to find it. And it has two authors, Dongwei and Yao. So maybe that'll be enough for you to find it.
I do have a question myself, a bit broader. In the end, you started from reinforcement learning, but your role is more about mathematical formulation, how to solve that kind of problem. Do you know if there are any other kind of fields or kind of problems where this kind of methodology can be used or should be used, in your opinion, because they have an advantage to your system?
Great question. Yeah, so this methodology being one where you reformulate these objectives using this conjugate form and then get this new objective that's easier to optimize by turning into this min-max-like thing.
Yeah.
Actually, the original work that we build on is from Bodai and others. And in fact, they were using it not really for reinforcement learning. They were generally saying, imagine you had an objective that has this annoying situation where you have an expectation and you have like a squared on the outside of the expectation. And now it's hard to actually optimize this. So they have different examples where they then applied this conjugate form. One of those examples is in fact one reinforced learning example, but they were more interested in some other examples as well. So if you wanted to find that paper, it is called, okay, the main author is Bodai and the name of the paper is like conditional embeddings. I think if you look up conjugate forms and conditional embeddings, you'll finally find it. So they have some cool examples there.
Okay.
So I do think it's a really cool technology introduced by that group that we have then taken and said, thank you very much, and specialized it to our setting.
Okay. Thank you very much. Well, I think time is up. So I would wrap this. So thank you very much, Martha, for the very interesting talk and very thorough answers as well. Thank you everyone for your questions, and thanks Janiel for facilitating the discussion. And as a reminder, this talk will be uploaded to our YouTube channel, where we can also find all of the other talks that we had in the past. So again, thank you very much and take care.
Thanks, everyone. Thanks for listening to me about
Thanks.
this topic. As you can
Thank you,
tell, I
Maria.
love it.